Ever wonder how your phone or computer instantly knows what language you're typing in? It's not magic, it's language identification, and the methods behind it are more fascinating than you might think. Today, we're diving into a groundbreaking approach that's simpler, more transparent, and way more flexible than traditional AI models. Let's start with the basics. Most language detection systems today rely on AI, like the big neural networks that power tools such as DeepL or Google Translate. But here's the thing, those models are black boxes. You can't easily tweak them. They need massive amounts of data, and it's hard to understand why they make certain decisions. This research offers a different path. Their method uses three key advantages that make it a game changer. First, modifiability. Think of it like a recipe. If you want to adjust how the system works, you don't need to retrain the entire model from scratch. Just tweak the rules and you're done. Second, minimal data requirements. Unlike AI, which gobbles up huge datasets, this approach only needs basic info. Lists of common characters, how accents work in different languages, and patterns of letter pairs, called bigrams. It's like having a cheat sheet instead of a textbook. But the biggest win: transparency. With AI, you're trusting a black box to make decisions. This system, you can audit every step. Want to know why it guessed Spanish over Italian? Follow the logic, no guessing, no hidden layers. That's huge for applications where accountability matters, like security systems or academic research. Now let's get technical. The core idea is frequency analysis, counting how often certain letters or patterns appear. For example, in English, you'll see lots of E's and T's, while in Spanish, and tilde is a dead giveaway. But what happens when text gets noisy? Maybe someone accidentally deletes a vowel, replaces a letter with a symbol, or adds random characters. Here's where things get tricky. The researchers showed that noise operations like these systematically lower the score of the most common characters. Think of it like a scoreboard. If you remove or replace high-frequency letters, the overall score drops. They use the L1 norm, a mathematical tool that sums all character frequencies, to prove this. If a vowel like E gets deleted, its score vanishes. If a new, less common character sneaks into the top 10, it can't compensate because it's not as frequent. The same logic applies to substitutions. Replacing a vowel with a consonant or symbol usually hurts the score. The math shows these changes always lead to a lower total score, which messes up the algorithm's ability to guess the language. But the researchers didn't stop there. They built a smarter system to fix this problem. Their final algorithm uses two key tricks. 1. Diacritic bonuses. For short texts, extra points are given if there are lots of accented characters, like French umlaut or German sharpesse. This helps when there's not enough text to rely on regular frequency stats. 2. Bigram scoring. Instead of just looking at single letters, the algorithm checks pairs of letters like TH in English or CH in Spanish. This is super helpful for languages that look similar, like Dutch and English. The result? Their method achieved 100% accuracy on tested datasets, way better than older approaches. They even proved mathematically that their scoring system works like a norm, meaning it's reliable and consistent. But here's the kicker: this isn't some black box AI. It's all about patterns, probabilities, and clever math. And because it's lightweight, it runs fast, even on basic devices. Let's talk about the math behind it. The team used the Minkowski norm, a generalization of the Euclidean distance, to measure how close a text's letter frequencies are to known language profiles. Imagine comparing a text's fingerprint, based on monograms and bigrams, to a database of language profiles. The smaller the Minkowski distance, the more likely the text matches that language. For example, a Romanian text with letter 219 and letter 21b would have a distinct fingerprint compared to English, which relies on E's and T's. They tested their method on a variety of texts: fairy tales, poems, even historical documents. For texts longer than 150 characters, their approach was 100% accurate. For shorter texts like social media snippets, it still nailed over 80% of cases. That's impressive, especially since their method doesn't need massive datasets or powerful computers. But no method is perfect. Short texts or ones with typos, slang, or missing accents can trip things up. However, for longer formal texts, this approach is robust and efficient. It's like having a lightweight tool that's surprisingly effective, perfect for situations where AI might be too slow or resource-heavy. So why does this matter? In a world where AI is everywhere, having a lightweight, explainable alternative is a breath of fresh air. It's not about replacing AI. It's about giving developers and researchers a tool that's fast, flexible, and honest. The future? They're already planning to expand this to support UTF-32, a character encoding that handles way more languages. Think ancient scripts, emoji, even fictional languages. Imagine a world where your device can recognize any language, no matter how rare, just by updating a few rules. Next time you type a sentence, remember, behind the scenes, a battle between complex AI and clever, simple systems like this one is happening. And sometimes the underdog wins. Thanks for watching. If you want to explore how this works in practice, check the links in the description. And don't forget to like, subscribe, and hit that bell for more deep dives into the science behind the tech. See you next time.